But the goal of the class is to put the number of the observations, the things we talked about. We mentioned some geology around the here and there, and I think it might be useful just to make sure that you get a sense when you look at this map of North America and notice the beautiful background that that Zoom allows you to use. We're going to look at North America and get you a flavor of where things are in the context of the geography and sort of what makes this continent, what puts this continent together. Obviously, it's not going to be an exhaustive class on the geology of North America, but it is going to be a class where, hold on one second. Okay, no, that is recording. Where I want to sort of get you a sense of when you look at the map where things are. So use that same map, but I labeled a few things that are that we're going to focus on. Obviously I recognize North America. This map is called Time and Terrane, which is a map that tries to look at geologic realms, geologic areas, but also puts the time part of those geologic areas. And so it combines the tectonic setting and the time of these events. So it's actually quite a powerful and informative map. And it is not a geologic map in the sense that it shows formations. It just groups them all into these time blocks. And we'll talk about time in a second. But if you look at the map of North America, then you would immediately sort of start to be drawn into the red color. That's up in the Canadian side mostly. That's the oldest rocks that North America preserved, and we call that the shield. And that's the internal, that strong, that cratonic part that we talked about. That is the core of North America and some of the other continents like Africa, for example. And that's what the S is. So the shield is the first one that jumps at you. Now, in our side of North America, so in the US side, we find the shield as well, but it's covered by a thin veneer of rocks. And that's usually carbonates. If you drive around here, you'll see the outcrops here and there of these carbonates. And that's that little P there that I marked up. That's, we call it the platform sequence. It's not a very thick, it can be a kilometer thick in a few places, but usually it's much less than a kilometer thick deposits that are, in our case, all Phanerozoic in age, mostly Paleozoic in age. But underneath that, you would find the shield as you go there. So that's the platform sequence. There's an interesting feature, a hugely interesting feature in North America, what makes us one of the continents that have some characteristics that sort of tell plate tectonics, well, the whole story is not complete. And we'll touch on that. And luckily, that's one of the fantastic things, the geology of Michigan. There's not much to show you, but it has actually an incredibly interesting geologic history, because there's a nearly 5 kilometer deep basin that is in the Paleozoic that sits right in the middle of this plate, this continent, and that hole in the continent that's sunk down 5 kilometers depth, and that's a lot of depositional environment, and it's in the middle of this rigid plate. So this is not a plate boundary, this just happens in the middle of that plate. We call it intracratonic basin. So we'll touch on that at the end, see how much time I have as we get through these various classes. The other ones that, of course, that are the features that are the most pronounced features, then when you look at the map, especially if you look at topography, is labeled with the O. That is the orogenic belts that we can still recognize as such. The Cordillera, we'll start with that on the western side. It's particularly well exposed in Canada. It makes up all of BC as you go up into Alaska as well. But there's also some good segments of it up in the US, as we'll touch on a little bit later on. On the eastern side of the continent, we find let me close my door. On the eastern side of the continent, we find an older origin, the Appalachians. We'll touch on that, of course, as well. But it's an origin which is no longer active today, but it's still recognizable as such. And that's where our field trip would have gone and stuff that I showed you. I'll touch on the extended crust over here. That's something that's an unusual extension that takes place in the southwestern US. That is not a characteristic we see all around the world. It's fairly unique for the US, but it's actually quite interesting for different reasons of how you actually extend and break up the crust. And then what you have left, we also have, by the way, sorry, we also have it in the southern part of the continent, the Gulf Coast. We have some extension there in that region. That's where the source of the oil. Deep drilling is targeted there because that's the right rocks for carbon. And then on the East Coast, so beyond the Appalachians, where so like Florida and the Carolinas, we have these flat-lying young deposits That's just what we call the passive margin deposits, meaning there's nothing, it's a margin of the continent, margin meaning it abuts the ocean. It's not a plate boundary, there's just deposition taking place, and that's the plate margin on that map. And so I've marked them all up. I'll circle a margin as well because I have that capability now. So those are the characteristic features of when you look at the continent of North America. And I didn't mark up all the other places, but most of these other places are all very similar. They all fall in those basic realms. The peak would go all the way up to the frontal part of the Rockies, etc. And so that gives you the first sense. And I hope that you would see this map and start to get a story out of this map as it goes forward. The other characteristic that we have to briefly touch on is this the fact that, of course, geologic time is long. We've talked about deformation. We never talk much about how long it takes to deform rocks and to do the thing. And what this shows is just the time scale that we now, there's the updated time scale from the GSA updates that every now and then that gives us the sense. If you want to be sort of a memorization exercise, well, enjoy this one. There are lots of names. Some things are very familiar, others are not. But the one thing you should really have a good sense of, I think, as a geologist in general, is the big breakdown, the breakdown that we find in the Cenozoic, the Mesozoic, the Paleozoic, and the Precambrian times. So the Cenozoic boundary with the Mesozoic, 65 million years. You remember that? The dinosaur extinction window. The Mesozoic and the Paleozoic boundary is around 250 million years. I round off these numbers. And there's specific numbers I find that not useful because it's good to have a general sense. Whether it's 251, what it should be, depending on who you ask. But 250 is good enough. Boundary Mesozoic and Paleozoic. By the way, that's also a big extinction event. It is the largest extinction event that we have seen on the planet so far. The base of the Paleozoic is nowadays located at 540 million years. That means that the Cambrian explosion of life happened at that time, so 540 million years ago. Now, what's interesting to remember now, of course, is that remains another 4 billion years of Earth history is not covered by these first three eons. And so the Precambrian time, we lump it as the Precambrian, is this window of that goes all the way back to the beginning of the Earth, 45, 60 million years. We break that down in eons, the Proterozoic and the Archean and the Hadean. This is not the class to talk about, but you need to have a sense. 65, 250, 540, and 4560. These are numbers that should sort of in the back of your mind. It makes geology the amazing feature that it is. And we'll look at features that are characterized by Cenozoic, Mesozoic history of North America, Paleozoic history, and the Precambrian history. That's how we're going to break up this class as we talk our way through these features. So this is another thing that you might eventually want to print out or hang up somewhere on the wall. It's always handy to look back. And rest assured that 99% of the geologists, we need to go back into the time scale to find out the details, right? Most people know their little favorite area. I mean, I've worked a lot on the Eocene, and I know that sort of around 50 million years is what the Eocene sits. But most people do not memorize this. But it's nice to know Cambrian, Ordovician, Silurian, Devonian, Permian, Devonian, Carboniferous, Permian. You can memorize these things. They're useful, but it's hard to put the numbers with that. And the stratigraphy is important, but I want you to get the time sense of these origins, because we're going to look at North America. The stuff behind me, we're going to look at the Paleozoic, the Cenozoic, Mesozoic one, and we're looking at the other side. I should use my other. Oh, I have to worry about this. How this works in the mirror image, the Paleozoic one. Okay, right. Let's look at the western side of North America. I made a list of we discuss. I will not discuss all these things. There's no time to get to all these details and all these features. But I do want you to get a flavor of the things that are useful to think about. We'll touch on these things in a light way. We'll look a bit at the terrains. We'll look at the arc system. We look at the transition to extension, and even the San Andreas fault we'll mention again at the end, the extensional boundary that characterizes the western side of North America. Okay, So I put this map up every now and then so that it burns in your mind what we're going to talk about. So we're going to focus first on this section right over here of the country. That's the western side of North America. We can generally call it the Cordilleran system, but there's a lot of features that are in addition to the Cordilleran. And the time on the side shows you that these yellowish colors is really what we are talking about. So the yellowish and the greenish colors represent the western side because that's the Cenozoic and that's the Mesozoic. Okay, I immediately put this up to get you a flavor of what happened in that Mesozoic to today. This is a map that is an analysis that was done on these on PaleoMap with Chris Cortese, but it actually tracks the arrows are the motion of the plates over time. And so the continents obviously move around, but you see, interestingly enough, that North America, right over here, is actually moving in a westerly direction, even though the Pacific is subducting underneath that. And so you get the sense that the plates, of course, are not sitting there passively and get subduction zones, but also the plates are moving relative to one another. And that will come back later on. And I know that my signal, I should probably find a way to erase that annotating function there. Okay, clean it up. The location of margins also evolves in this absolute reference frame. So that was the animation, and the pictures on the side are the snapshots that Chris created that were actually what the map was based on. That we drew that map, and so it's a history. The Mesozoic and the Cenozoic is the history of the opening. I'll run it one more time when I say that. It's the history of the opening of the Atlantic Ocean. That is really the characteristic feature of this part that we live in. And in this case, the eastern part of the configuration, it's the closure of what we call the Tethys Ocean basin. That's the ocean over here is called Tethys. Sorry. That's the ocean basin that's between India, in this case you see that now India rapidly closing, and Asia. And so that ocean basin is gone. The Indian Ocean, as we know it, gets formed, and the Atlantic Ocean gets formed. They weren't there before in that configuration. So that's the characteristic feature for understanding the Mesozoic and the Cenozoic, and everything that happens reflects that particular part of the history as we go in there. See where my mouse goes. Oh, right over here. All right, now look at the geologic map. It's incredibly rich in areas, meaning we found a lot of features there that look like they sometimes were very much disconnected. And remember, the characteristic feature that Mark made up the Cordillera of North America was this concept of that there are these areas, there are these terranes, as we call them, that have inherently a good story to tell. They all have a consistent geology, but then you step across a fault zone and suddenly you're in an area which is completely different. I mean, a complete different geology. The lithologies, the ages are different. And then you do a little work and you step over a fault zone and you go into another zone. And so what we discovered at North America, the Cordillera of North America, to a large extent, all these colors that you see, the greenish and the reddish colors, these are all terranes. These are blocks that were welded on to the North American margin as part of this opening of the Atlantic and closure of this and convergence of the Fuca plate, a smaller plate segment that was sort of being subducted underneath. And so all the geology of Alaska and all the colors that you see below the bluish and purplish color, these are all elements that were not part of North America. This is all added on. These are those terranes. And you see some names in them there. Stickeen terrane. We talked about the one thing that we talked about was this Wrangellia terrane. That's what I mentioned in class specifically. It was also the first one to really be identified, and we find it in different spots. We find it in the U.S. We find it in Vancouver Island. We find it all the way up into the Wrangell Mountains of Alaska. That's where they were first defined, and then people discovered that these same rocks were found all along the margin of North America. And so the first characteristic feature of North America was this idea that we have these terranes, and this is the map that I showed you. It's a little less busy, although it still has the same names of all these terranes. And as you have this closure, this subduction that takes place on the North America, the terrains that were sitting on the subducting plate came in obliquely, not orthogonally, but they came in, here's the margin, and they came in obliquely to that margin. And as they do so, once they got that margin, they were not subductible. They could not go down because they were buoyant. And as a consequence, these terrains got torn up, got cut up by these large-scale transcurrent faults that characterize the geology of the Cordillera. And that was the signature observation. You found terrains, blocks that were internally consistent, and then was a block next to it that had a completely different history. But the boundary between those two blocks are typically these large-scale lateral slip or strike slip faults. And so this is transcurrent faults is the characteristic feature that allowed it to be spread out all along the margin of North America. So the Cordilleran terrains are very complicated because, first of all, there are multiple of them. People argue how many of them, but they're not 50. People said there were 50 or 60 and a lot of terrains. No, many of these terrains were the same. It just turned out they were spread out over a very large area. And that's why it looks it's a jigsaw puzzle where the pieces are being cut up again and spread around along the site. It took us a while to figure it out. But once we figured it out, we knew what to look for. We looked for similarities, even though they were otherwise very far apart, these areas. It was incredibly insightful, and it changed our thinking about orogenic systems. We realized that you have to work along the trend of an origin to understand it as that goes forward. So terrains, characteristic feature, the Cordillera. Turns out to be characteristic for all origins. We now start to, we've applied that everywhere else. The other thing that's a feature that we're not going to spend a lot of time on, other classes do that, of course, is that we have subduction zones. Then we have also, typically, we get arc systems to go with that. And we find, of course, in North America, ample evidence for that process that also formed the terrains, but also the process of subduction. We find all these magmatic arcs, and we typically find that they're exhumed. These are Mesozoic arcs, and Yosemite is a good example. Half Dome, I think that's Half Dome up there. Yeah, probably. Actually, I don't know. It's El Capitan, probably. It's El Capitan. Half Dome is rounder at the top. So that's just this big, exhumed, deeper part of a volcanic system. The volcanic system that sits at the top, that used to be right up here, is being eroded off, and now we're actually seeing the deeper part, the magma chamber system. So it's the Sierras are like that. The Cascades are like that. On the map on the right, the black areas is the Sierras. We find these preservation of these blocks. This is just the exhumed volcanic system. Today, there's no active volcanism in the southern U.S. In most of the U.S. in many ways, until you get to the northern part of the U.S. and all into Canada. Of course, we get the subduction system. Mount St. Helens and the like are the active volcanoes today. They are marked right up here. These are the active volcano chain. That is the modern volcanoes. The granite batholiths that you see in many of the parks are the exhumed older system when we had this Mesozoic, particular Cretaceous subduction going on. So the arc is present too. It's older in some places. It's young today. It continues today. The process has been going on for quite a long time. Now, the structural feature that's particularly fun to look at is the fact that we have these terrains we talked about. But if you go more to the east, then we get this beautiful frontal thrust belt that is the Rocky Mountains, the familiar Rocky Mountains that make these beautiful ranges in the U.S. and make these spectacular limestone cliffs in the Canadian segment. And again, on that map that we showed before, you can see the mountain system that runs right through here, comes up through here, and comes down there and goes down way. And it peters out in the south because the extension takes over, so it changes feature in the south. Now, you do field camp. Maybe that's not a nice thing to mention now because field camp is not going to happen. We're sitting right up here. Michigan's field camp sits right up there in Wyoming. But the Rocky Mountains are the poster child of understanding the evolution of orogenic fault thrust belts. And so we'll take a picture there. We spent quite a bit of time on this, but I often did not play it into the context. If you hear a strange snoring sound, it's my dog sleeping next to me. She actually snores, or she dreams sometimes. So I'm sorry about the background. Psst, Luca. Thank you. Sorry, woke her up. She falls asleep again in 1 minute. She's not worried about that. The Rocky Mountains, and so here's the picture of that area that it would be very familiar for a field camp. And at the bottom end is that very busy diagram that I told you about, is that as you have a thrust and you have a new thrust, the thrusts are one after the other. The thrusts are multiple of these thrusts, as you can see in there. They'll step away and they come up, and there's many of them in there. And they follow the nice, generally follow the nice system whereby the most easterly thrust are the youngest thrusts. So we talked about the piggyback that takes place. We also talked about the fact that you have these ramp anticlines, these fault bend folds. Many of them you see in this diagram over here as a good example. So actually right up here, and so we see those structures are very well developed in this cross section. This is a cross section just south of where our field camp sits. Our field camp sits right up here in this area right up here. And so you see now all these features now in their real setting. The fallen thrust belt takes thin veneer, not high-grade rocks, they're low-grade rocks. They're just sliced up the cover. It's pushing snow. So there's somewhere from that side over here, there's a big push. That push, of course, is the terranes that are being accreted on the western side, and that pushes the fallen thrust belt and gives this nice geometry. It's more complication than what I'm saying, and aficionados will immediately jump up because it's actually a very large, far regional extent. Orogen has some own questions why that is. But the basic story is completely what I said. It is a bulldozer in the west that pushes things and moves it up to in this easterly direction according to the rules that we have. And the picture of Lewis thrust is one of the frontal ones, one of the most frontal ones. It would not be on this map. The Lewis thrust sits a little bit higher up. You have to go into, I can't see it very well, somewhere over here. But the Lewis thrust is a good example of the most frontal thrust. It's Eocene in age. We dated that with clay, with clays in the fault zone. And if you go there, it's Glacier Park, and it's one of these klippen that are preserved. It's the eroded remnant of this big thrust that otherwise is not present except at the base there. As we look at that, it's again limestone. The limestones are usually very strong. They usually stay. This is a Precambrian limestone, however, and that sits on this Cretaceous sandstone. So it's a deeply cut thrust system. The Rocky Mountains. Okay, that's the feature that we talked about in the context of geometry. So what else? Well, it becomes actually one of the amazing features of this map of North America. And you have to look a little bit carefully at this map, and I put a little square around it. I put a circle around it as well. You see these reddish colors that are popping up as sort of like raisins in this sea of yellow. And remember that the red, excuse me, represents the old part, Precambrian part of this map. That's the big strong red color. Oops, the red color behind me over here. That's sort of the older part. And you see these things coming up also in the middle of this sequence that is in the foreland part of the Rocky Mountains. Right, we are slightly away from the Rocky Mountains. This inset map right here is the Rocky Mountain front. And then we see these features that are to the east of that: the Wind Rivers, the Black Hills, the Bighorn. Some of them you've seen. Some of them are used as monuments, as you know. And those are Precambrian rocks that are also structurally brought up to the surface, but in a surprising manner. We call this basement uplifts, because we have faults that apparently are very, very, very deep. They go to great depth. They cut all the way through, all the way through the Moho. So these fault systems may be as much as 40 kilometers depth. And what they do, if you crudely draw this line through here, fault zones, of course, are not a perfect zone. But what you have is that these blocks of Precambrian rocks are brought up, pushed up by reverse faulting. But this reverse faulting is opposite in direction to what we see in the Rockies. So these reverse faults are moving. The hanging wall moves now to the west relative to the footwall, whereas in the Rockies, the hanging wall is moving to the east. Why are they there? Well, we think what happened was that the configuration of the subduction system changed so much that the stress started to fracture, started to form these reverse faults way inland, way inboard, away from the subduction zone. But underneath, the mantle underneath changed its behavior, it changed its strength, and so much that we started to break pieces off. And so really what you should think about is these are small thrust fronts. There's it here, it goes right again here, that are bringing these rocks up, and they're moving these rocks relatively in this direction over here. That still means that relatively we're moving North America and is overriding the subduction system, but it's one of those amazing features. The Wind Rivers, the classic area, but you're of course familiar with the Black Hills, and as I said, that's where the monuments are. Precambrian is the key rock there. We do not bring up a lot of Precambrian rocks that way all through the country, but in that part of the world we do. It tells us something about the deeper connection between the mantle, the subduction system, and the crust as it exposed. So basement uplifts is a good term for them. As long as you realize these are on reverse faults, these are not vertical faults. These are steep reverse faults. They're not terribly steep, sort of 30 degrees or so. But they bring these rocks up. The geologists in the area would call that laramide deformation. That's a term that you often hear, laramide style deformation. Descriptive term for that simply being basement uplifts over reverse faults. That's what that really means as a term. So that's the word laramide. It's a geometric name, although it's sometimes misused as a time name as well. There's no laramide time. It's a laramide style deformation. All right. Now, if we then move on a little bit, so we will look at this area over here. Now we're going to start to move on. We're looking that part of the world. We start to see that there is a younger feature that overprints all this history, that sort of starts at the end of this full thrust belt formation and these laramide basement core uplifts. We start to see that the Western US starts to break apart. We actually extending the Western US. We start to see that there's this what we talk called basin and range extension, all these areas whereby we have highs and lows and highs and lows, and we looked at these geometries. And so what we find is that overprinting this history in the younger part, now we're in the Cenozoic, so we're now starting somewhere in the Miocene in particular, but we're starting in the Cenozoic, middle of the Cenozoic. We start to see that North America, at least that part of North America, not the other part, but the part that's also south of where the subduction still takes place. So it's in the part where we are away from modern subduction. We see that area is extending. Again, why is that extending? It's an unusual feature. It's a lot of talk about it in the US because it's in the US and a lot of people work on it and everybody has gone to these areas and everybody does their research in it. We had a great dating project in that area. But it is quite unusual. And again, it probably reflects the fact that there is an interaction between the plate subduction that took place and the upper part of the lithosphere, making for this unusual regional extension effect that is called the basin and range extension. There are no other places in the world today that show this kind of geology. Even the extension in the Arabian Peninsula that we talked about, which is opened the Red Sea, that is not so widespread. This is a very large extension and continues today. It's the source of some of the recent earthquakes. The Ridgecrest earthquake that took place was a pair of two earthquakes. One earthquake was this basin and range type extension, and the other earthquake reflected the San Andreas fault that we'll talk about in the next slide as we go forward. But just to refresh your memory of the geology of these things, this is what these metamorphic core complexes were about. We talked about regional extension. We talked about continental extension. This is the area where we have these low angle normal faults. It's extension, so it's normal faulting. And we even found in places that we brought up these the deeper underlying geology, because as you start to remove the top, you start to, by isostatic rebound, you start to bring up the deeper part, and you find these places that the deformed rocks and the rocks that are at greater depth, sometimes the Precambrian, are being brought to the surface. Metamorphic core complexes was the term that people coined before they understood them. So now we understand how they work. So that's why that area sits in. So that's the younger history. That's the Cenozoic history of continental extension that takes place in southwestern US. We do not see that as we go north in the US. We see it a little bit There's some faint pieces left in the most northern part of the Rockies, but as you go into Canada, it's essentially it's a few places maybe, but it's essentially we don't find that. So it is really a localized effect, reflecting the type of subduction that takes place with time. It's not enough to explain all the details, but there is always this interaction between the plate going down and the overlying part, and in this case, it gave that structure. All right, now one more feature that we talked about. I play the animation. That's Tanya Atwater's animation. That's the fact that we have some additional things, is that as we have the subduction going on, we were eating up the ridge, and we're eating up the rich connectors, the transform fault. And so the San Andreas fault system is the representation of the fact that we're steadily eating up the ridge that separated the Juan de Fuca plate. Farallon plate is called here. Sorry, it's Juan de Fuca plate now in the northern part. But the Farallon plate used to be very large, and the Pacific plate, but North America is moving over its own ridge system, over that ridge system. And as it does so, the connectors between the ridge segments are now on land. They're underneath California, and they still connect onwards from the Gulf of California up to just sort of off Oregon. And that's what the San Andreas fault is. That's the youngest part. The history. Extension still continues, but now we added about 20 million years ago the history of the San Andreas fault evolution. Very unique. But you can now start to see how complicated the geology is in that part of the world. We have a lot of these features that go with that. Okay, we talked about all these things. That's the context I want to place them in. I just put this map up to give you a flavor and a bit of a shout out. It's fun to go to the UNAFCO site. You can actually, nowadays with GPS, we have real-time meaning. We can actually measure the displacements, and they are on the order of centimeters a year, which is what the characteristic feature is. But along the San Andreas fault, they're on the order of 5 centimeters a year. The length of these arrows is the amount of displacement on a yearly basis. And so this shows not only the amount of displacement, but also the relative displacement based on a geostationary reference frame that, of course, is in the sky that we look at. So remarkable, nice coherence in those features. It's dominated, as you can see, by the San Andreas fault in North America. The long northwest to southeast lines are the San Andreas system. But if you dig a little bit deeper and look at these arrows over here, that's the memory of the extension that still continues today as well. Hence the Ridgecrest, one of the Ridgecrest faults that takes forward. So it's fun to go there and have a look at that. And we have instrumented the country unbelievably, so we can have these real-time measurements as we go forward. Okay, let's go to a new segment. Let me move my own slides forward so I know where I am in my slide system. There we go. So let's have a look at another part. This map again. Try to get you the flavor of where we're going to jump forward. So we're going to go now and look at the eastern side of the country. The Appalachians. That's the name that we give that mountain belt. It's a mountain belt that is Paleozoic in age. Now, what that mountain belt represents is another part of the history. In history, before the Cordillera were there were no Cordillera mountains when this history took place. It's a very interesting mountain belt, obviously, because we live nearby it, but it's also the first mountain belt where we applied modern plate tectonics to understand ancient tectonics. It's the first place where people were able to start to use the tools that you had learned in the class so far, that we talked about, the tools the identifiable features, accretionary wedges, ophiolites, arcs, all these features that are characteristic of modern plate tectonics. People applied that to this old mountain belt but there's nothing active anymore, and they found all these features. They found the old trench fill deposits, they found the accretionary wedge, they found the island arc system, all of that long quiet geologically, not active anymore, but they were preserved. So it's really revolutionized plate tectonics in the sense of not only understanding the things today, but it said you can apply this now to old systems and see whether the modern observation of tectonics holds in the past. And it turned out it holds extremely well. Plate tectonics works for a long time in the same way on our planet. And so that's what these write-ups are as we go forward. Now, It's again to get your bearings. We move now into this window, this the Paleozoic window of no, never mind. The eraser does not work on this thing, I think. No, oh it does. Oh, it does. Turn it over. We're going to look at the Paleozoic part of the history. It also, we looked at the Appalachians because that's where we found the best evidence for fossils that help us understand the explosion of life. That's really what started much of this thinking. And in the UK, in Wales in particular, is a beautiful sequence of the lowest part of the Paleozoic with a lot of fossils, and we learn a lot. So we're looking at the history that goes back to the beginning of the Paleozoic. I put this picture up to remind you of something that all now what we have is evidence that is no longer related to ocean floors. We have the ocean floors that we see today have a memory of their evolution. The ocean floor stripes you learned up in the intro class. But the ocean that we talk about here, the separation of the continents, these oceans are long gone. They no longer exist. So how do we know there were oceans? Well, this is where the fossil record comes in. The fossil record told us that there are places where there were continental margin systems where animals were living, but they did not communicate. It was too far apart, apparently, for some critters, like for example, trilobites, to get their way from one side, one continent, to another continent. Got to see my own hands. They don't actually. It's interesting. You don't see the hands until you move them. They were using fossils to understand the separation of continental blocks, and these fossils. The classic ones, of course, I brought it in an example, are trilobites, because they were the first to really puzzle us. And what puzzled us was that there were trilobites that you find up in Newfoundland, and you find them up in New England on the most ocean side. We found this trilobite that looked like nothing of the other trilobites that we find in Cambrian rocks in North America. And it actually puzzled people so much that they called that trilobite Paradoxides, from paradox. Why is it there? And it was not resolved for a very, very long time until people started to realize that, wait a second, we find that same trilobite also at the African side of today's plate configuration, meaning that it looked like that trilobite was living on North America side and on the African side. And of course, what we figured out, that plate tectonics, which is what made this argument so powerful, told us that, of course, plate configuration were very different. North America and Africa, right over here, were fully in contact to one another in the Pangea configuration, but in the Cambrian times, they were widely apart. And so we find fossils here that are different from fossils that are here, where we found that other blocks in between had the same feature. So we could start to use fossils to understand the separation, but also when things were close enough to have communications. Another technique which really revolutionized plate tectonics is paleomagnetism, whereby we use the magnetic field, the memory of the Earth's magnetic field in rocks to understand their location. That really was in the late 50s, the first time that applied, early 60s. That was a complete new line of science that helped us understand geometry, because the rocks told us where they were at a certain time. And they told us that they were not where they are today. And so fossils and paleomagnetism were the tools to do the paleogeography, to make these maps that we showed in many of the animations. But we have no ocean floor magnetic anomalies. There are no ocean floor in place preserved. And so all this is based on that part of the history. I'm going to do the Appalachians a little bit quicker. Actually, I don't know how that's quicker or not, but I want to sort of get you the same sense. If you look at these mountain belts, here's a general map of the Appalachians, we start to see the same idea. We see what we call the North American part of it, which is the stuff closest to where we live. So that's that is the old part of North America, is recognized in the deposits that we call the North American realm. People call it Laurentia. That's the term that they use, but it's the North American realm. And then the other thing that we find is that if you go to places like Rhode Island and Nova Scotia and Newfoundland, so Newfoundland over here, Nova Scotia region, and in part of New England, we find elements that are what we call very much look like they are Africa-like. They look like also rocks that we find and fossils that we find in Africa. They are. The term for that is Gondwana. That's a term for Africa people use for that. But they're the Gondwanan realm, we call that. That's the fossiliferous realm. And then what beautifully is preserved, there's this orange and this green color in there. Those are various remnants of the ocean in between, and terrains that are in between, blocks that were on the ocean that was now long gone, that are just still preserved because they were not subductible. They're arc terrains. They're entire volcanic arcs that could not be subducted. They got welded on to the margin as that ocean that existed before the Atlantic, the proto-Atlantic Ocean, we call that. Iapetus is the term that the specialists use for that ocean. They call it the Iapetus Ocean. But these are the remnants that are in between, that are just all kinds of features: plateaus, oceanic islands, arc systems, smaller subcontinents that are found. And it fits exactly the story again that the Cordillera is. And these are terrains that were accreted. In this case, not very oblique, because they're not sliced up. They're usually terrains that have their own internal part. They're not terribly sliced up, at least. And you have this configuration of one margin, the North American margin, on one side, another margin on the other side, the remnant of it, and the stuff in between is just the remnants of the ocean basin. And all the way from Alabama in the southern part to Newfoundland, we can see that that geology there. It's a remarkably well preserved and continuous sequence, in part because it doesn't have that huge obliquity. But it's a little bit more complicated, as we've seen a little bit in the southern Appalachians. But that's the general setting of the Appalachian origin. Now, the cool thing here is that I talked about the fact that these are oceanic realms. These are features for oceans that are preserved. But what is the cool thing is that we actually find evidence. We find rocks that are preserved that tell us that there was once an oceanic sequence in between. There was once rocks that represent the ocean lithosphere. And right over here, where the arrow is, in this park right over here, Grossmoorn Park in Newfoundland. If you go there, it's very strange. It's sorry, I can't show you samples. I have the samples, but the rocks there have this rusty. Well, basically, they're very not pretty. They're ugly. They're rusted rocks. What they are, these are iron-rich mantle rocks that, of course, as they got exhumed, iron reacted with oxygen and rusted. It's just a rust-looking feature. But that's the lowest part of the oceanic lithosphere sequence that had, remember, it had basalts at the top, it had sheeted dikes, it had gabbros, and then it had ultramafics peridotite. Here, this is the picture of the peridotite part of that sequence, where we have these rocks preserved of the lithosphere of the lowest part. Now, why is this so interesting? This is lower Ordovicium. This is 480 million years old. This is ocean floor that is, of course, is no longer there, but in a few places the ocean floor got pushed in an orogenic system on the continental margin, and therefore it got preserved. It didn't get eroded off, but it also actually did not get subducted. It was just a small sliver that was pushed in. We also find that same sliver like that in the English side in the UK, where it's called the Caledonites. And less so in Scandinavia, there it's more higher grade rocks, but they discovered the exact same age and the same oceanic signature in rocks in the UK side. A place called Ballantrae, it was the first place where it was well described. So here we are, a memory of oceans that are no longer present. A few slivers of them are preserved. These are the ophiolite sequences that we were after, that we targeted to get a sense of. Those are the ones that tell us that there are ancient oceans. And this is a remarkable one because it just basically didn't get eroded either, and it's just a lot of mantle rock sitting at the surface. Not pretty, but we don't have a lot of mantle rock. This is one of the places where we have a lot of mantle rock. It's not as well preserved in other places along the Appalachians. This is by far the best place to see that. There are also excellent pieces of oceanic lithosphere preserved right up there, and the other slivers that are preserved in there. So it's quite a remarkable observation. It allowed people to apply modern plate tectonics to the ancient times as we go forward. So geology, looking at rocks. Now we can actually put it in context. The question is, why don't we have the same spectacular outcrops in the U.S. part of the Appalachians? So we go to that part. It's because as we go to the southern Appalachians, so the part where, I'll be doing my hands right again, I can't do that, the southern part of the Appalachians, there we find probably the same early history, but it's completely overwhelmed by a very late deformation cycle in the Appalachians that generated very large thrust faults, gigantic thrust faults that shoved a major amount of the sequence on top of North America, much more so even than the Rocky Mountains. The displacements here are enormous. And so I draw this line over here. An enormous length, hundreds of kilometers long, of a thrust fault that took most of the southern Appalachians and moved it over the rocks underneath, the shield rocks that are underneath, and it gave the large Appalachian thrust system. We call that the regional Appalachian detachment, and so the rocks that were once there were overridden by this large amount of displacement. We didn't see that very well. There were a few indications of that. A few indications were that people were working in some areas, and they were actually looking at rocks, and they found relatively high-grade rocks that were overlying unmetamorphosed limestones. Well, remember, that was sort of not likely. You don't have high-grade rocks that are older overlying younger rocks that are lower grade. So they assumed that there were already reverse faults there. And that idea was already embedded for a long time. Called the window. Remember, the window that erodes into and cuts through the reverse fault system. But it was not until we used seismic techniques, when we used techniques that all companies are using to understand the deepest structure. Although in this case, we were not looking at the fine granularity that all companies use, but we're looking at the deepest structure. People set up a system whereby they generated local earthquakes, thumpers. They used these trucks that were bumping up and down, and they dropped the truck that generates an energy wave. The energy passes through the earth, and there's recorders along the way that sense the pathway of these waves. And in doing so, they could see the deepest structure, and they discovered this large scale detachment, and it is remarkable because it is so different from the northern Appalachians. But if you actually look into those blocks that have moved, you'd find features that fit the northern Appalachians. In this case, however, in the U.S. side, they are completely moved laterally in a westerly-like direction. And what it was is that is the point where the nose of Africa, where the bulb of Africa, pushed in against North America, and simply that collision, that promontory, as we called it at the time in our lectures, is where a lot of the shortening took place. Whereas in the northern part of the Appalachians, there wasn't that much late Paleozoic shortening. This is all late Paleozoic, Carboniferous in age as we go in these various features. So very different geology in detail, even though I first told you that the general outline is the same. Continental block, intervening ocean basin. In this case, that intervening ocean basin system has been shoved even more over the Laurentian continent, making for the geology. Again, however, it's quite easy to tease it apart and to understand the parts that go with that. So we no longer do these type of analyses. It's incredibly expensive to do. Also have to have a lot of permission and stuff like that. But it made us start to look at what's below the surface geology. How far does the surface geology extend down? Well, in this case, much to our pleasant surprise, especially with structural geologists, the surface geology really was a thin veneer. It turned out below that it was a completely different geology because we have these large-scale detachments that characterize that. And if on the field trip, and by the way, I posted the field trip. I have time on my hands too because things are different for me. I just sit down and do different things. I posted our field trip and do it. Let me know what you think. This is not high end. This is not a clever, beautiful, amazingly feature laden. But I wanted to show you the stops. I wanted to show you what we see at the stops, and I gave you brief descriptions of what we have at the stops. But I may do a voiceover, maybe not. I'm not that desperate to hear my voice all the time. But look at the field trip. All the features that you'd see there, all the structural features, are all Carboniferous features. They're all that late Paleozoic deformation that wrinkled everything in that area, including the beautiful fold structure that we find in Sightling Hill, this giant syncline that we have preserved there. Those structures are not found as you go into New England. They start to become very different. And then go into Canada, it's even less of those structures are preserved. Nice different way of looking at features. However, still the same. Terranes, thrusts, fault and thrust belts, all these features are there. I'm going to skip the orocline. Okay. I could say, of course, take a break for 10 minutes, but it's more a break for me than for you. And so bear with me. And as I just finish this off, as we go to the third domain, the third realm in North America, and then we have all these things together, and then we can do some stuff. If you have questions, please start to write them down, right? And do anonymously if you prefer, or your name, it doesn't matter. But that way I know what I can answer. I have the screen open here that shows the questions, so I can sort of see as they come in, and I can answer them a little bit later on. I will not open your voice or your video. We'll just do it all by typing. It's a little less disruptive with 24 of you, 25 or so online. Okay, so we've looked at the western side, the Cordilleran side. We looked at the eastern side, the Appalachian side. So we'll look now at the big internal side with this reddish color and this bluish tone that overlies that, the platform, and also a bit of that slightly younger stuff over here, although we're not going to spend much time on that. That's the erosional material from the evolving Cordillera. Underneath that is also shield, and so it's all platform type deposits, and so that's the segment in there. So let's have a look at those features. I call that the Continental Interior. Why? Well, it's because it's the continent and it's the interior. And here is the first thing that's so much fun. Most people that do plate tectonics only talk about plate boundaries. They always talk about all the action is at the plate boundaries, earthquakes, volcanoes, faults. Yes, that's true. It turns out when you look in North America geology, we found there's a lot of geology preserved in the interior. The geology is, first of all, the history of that interior itself, how it is formed. And we'll look at one example of that. The interior wasn't always an interior. It wasn't always a single block. So it has its own history of tectonics, how it got formed. But also, we have learned that the interior, the plate interior, is not a completely rigid, undeformable sequence. It is heavily deformed as well. Plate tectonics concentrates deformation at the plate boundaries, but it has considerable deformation still in the plate interior. And some of that is highly debated today. These are the unresolved issues today. And I could go on great length there. It's one of the areas that we worked on for many years, maybe another time, another class. But it's also the interior tells us that plates are not undeformable. The margins have most of the deformation. But the plate interior also seems to show quite a bit of deformation in addition to its own evolution. So the list of things we discuss are actually giving you examples of what happens in these plate interiors. And all these things we touched on already in the class as well. So again, it puts it into context, but I wanted you to get a flavor of where we are, just to make sure that you know where we are. Right? We're sitting somewhere over here. This area. You also noticed I really enjoy the markup that I can do with this. It hopefully makes it a little bit more alive than just staring at the screen and seeing my head bob back and forth. Again, the time frame. Now, why this is really becomes prominent, of course, we're talking now about much of that history of the plate of the continental interior is the history that is that Precambrian history. There's a lot of stuff happening in the 4 billion years that we have left in that particular that particular window. My dog thinks I've talked a lot now, and he wants to get some attention. And so we're going to look a bit at that. We're not going to look at the entire history. There's a lot to say about it, but I wanted to give you one flavor, one example of what plate tectonics in the past did, and also to highlight to you that it did about the same as it did now, except that the rocks preserved are different because we now are looking at the deeper part of the plate that's preserved. Erosion has taken off most of the top. The other feature that's important, it's trickier to work in the Precambrian because we no longer have the benefit of the fossil information. There's no shelly fossils that are after 600 million years, before 600 million years, I should say. We have no shelly fossils that help us do any kind of domains where these critters were living. And so we're left with only one tool, which is paleomagnetism, which is the position of the continental blocks relative to the poles as a tool to consider the location of the continents. And then we look, of course, at lithology, similarities, and times of deformation. So we have a pretty good story. Time, constraints, lithologic constraints, and paleomagnetism, but we no longer have the fossils. So as we go back in time, in the Mesozoic and the Cenozoic, we had ocean floor anomalies, fossils, and paleomagnetism. We go to the Paleozoic, we only had fossils and paleomagnetism. And if we now go into the Precambrian, we only have paleomagnetism left. And so our constraints are looser as we go back in time. And that's why it took us a little longer to get this story figured out. But the story is pretty nice and consistent. And just to give you a memory of what these plate interiors are like, remember this map I showed you a while ago, and look at the terms over here, the shield and the platform. And you can see that many of the continents that we call the continents have this interior, right? North America, much of Canada, and underneath the platform sequence, most of South America is an interior, a plate interior sequence. It's an old history that is preserved. Africa is all Precambrian in origin. It's the ages, the provinces in there. Western Europe, the Scandinavian sequence there, these are all, many of the parts there are Precambrian. Asia is an outlier there. Only in some parts do we find older part, but much of the action that we talked about in the Himalayas actually is the interaction that's all Mesozoic in age. But Australia, this is again a good one, is nearly all Precambrian. There's a few younger belts on the margins, in fact, just like North America does. In some ways, Australia is the mirror image of North America, whereby in Australia, these younger belts are on the eastern side, and in North America, the younger belts are on the western side. But Australia has a lot of history as well. And so to give you that flavor that this is not a North American thing, all the continents show this history. We just happen to have a lot of information because a lot of geologists were trumping around. And the nice thing is in Canada, there's relatively a lot of outcrop because vegetation is pretty brutal up north. And so vegetation is very thin. And so we're able to get good outcrops. But I wanted to focus on the US purposely. I wanted to sort of make sure that we get you a sense of the richness of the US as we talk about. And so as we focused on the Precambrian rocks, already I mentioned that there are these funny little blobs in there. I just marked up in this case, it's the Black Hills, but these are these laramide uplifts. Now they are young in their formation, but the rocks that are brought up there are actually these Precambrian rocks at the surface. But really the last good outcrops of that much wider extent of outcrops in Canada is found up in this Minnesota segment right up here. It's called the Superior because the whole tectonic domain is called the Superior Province. That's one of the names that we use for the Precambrian there. These are not time names. These are geologic entities, as we call these features there. But we do find that shield-like rocks, which is so rampant in Canada, we find some of that exposed up in the US. But much of the US, the rest of the US, if you look at this map, right over here, is all covered by this younger platform sequence. So it's underneath, we don't see it very well. Now, one feature that we'll focus on, we all mentioned before, is a feature that sits somewhere over here, which is a big pile of basalts, huge thickness, up to 20 kilometers thick basalts. It is an example of rifting, just like Africa is rifting today. A billion years ago, the North American continent was trying to rift in the same fashion. It never worked out because it never broke up, these two blocks. They just rifted, but it never became an oceanic system. It just remained a continental rift system. It got frozen in time. But it's a gigantic one. It shows that nature really tried, and a lot of lava is exhumed, but it did not really succeed in generating the rift history. We'll touch on that in a second as well. And then the last thing that we'll touch on, I just wanted to highlight that because that's our geology, that's our backdoor. I made these jokes that there's not much geology to look at in Michigan. First of all, that's not true. In the Upper Peninsula, we find Precambrian rocks, right? If you go to the UP, we find the little pieces left of what the rest of Canada has lots of, but we find interesting pieces there. Iron deposits are there. Copper deposits that are associated with the Mid-Continent Rift. We'll touch on those as well. But our part, the Lower Peninsula, is an amazingly weird feature. It has this giant basin, nearly 5 kilometer depth at the depot center right over here. Nearly 5 kilometers of sediments in the Paleozoic. We're filling up this sequence on top of the plate. It means the plate must have been underwater, obviously, otherwise you wouldn't have the depositional environment. But at the same time, that is not everywhere 5 kilometers, it's only there. And so those, we call them dimples. I like to call them dimples. These are giant basins that are found. We find it in Michigan is the best example. Illinois has one as well, but it's not as good. We always tell the University of Illinois that the Michigan basin is a whole lot better than the Illinois basin to look at. We'll touch on all these things. That's giving you the framework of these features. What marks the history of understanding the evolution of the plate interior? And permit me 1 minute to advance my slides so I can see the sequence of my slides as well in my own. There we go. What marks the much of that understanding of plate tectonics in the Precambrian was the realization that Pangaea, the supercontinent that is Paleozoic in age, late Paleozoic in age, is not a one-time event. It's not a unique event. We actually discovered, as we looked around, that it would seem that continental blocks had been organizing themselves into those what we call supercontinents more than just in the Pangaea times. And so the Precambrian gave us insight, because we have so many billions of years to look at. We're not limited to the 540 million years of the Phanerozoic. Now we have 4 billion years to look at this, that there were multiple of those supercontinents. I'll show you one which is extremely well defined now. That's a very well constrained, because it was the first major target we went after. That's called the Rodinia supercontinent. There was a supercontinent probably in between Rodinia and Pangaea. It's called the Gondwana supercontinent, but it may have been not as complete a supercontinent, but it doesn't matter. It gives you the flavor that there was another configuration where the plates were together. When we go back in time, we find that we have a supercontinent that is sort of at the early Proterozoic. It's called Nuna by some, Columbia by others, and even people have argued it gets thinner. The arguments, the evidence gets thinner. The evidence gets so thin it starts to look like one of those British crime shows whereby the smallest piece of hair was a whole story to solve the crime. We have even evidence that maybe at the Archean, there was an Archean supercontinent. That data, I'm not going to debate it here. It gets awfully thin, not because the geology is not good. There's not a lot of geology. There's not a lot of those old rocks that are preserved. But the key thing is the understanding the Precambrian geology made us realize that these supercontinents are features that are persistent and are found multiple times. And therefore, you can make the fun game that the future will also have a supercontinent. I showed you one example that's Chris Cortese and I put together. Chris wants to call it Pangaea Proxima. But you could argue that as opposed to closing the Atlantic, you actually close the Pacific Ocean, and some others have done that. And if you join America and Asia, and remember, geology are funny people. If you combine America and Asia, you close the Pacific Ocean in between, you get a new supercontinent that is called, wait for it, Mesia. Indeed, very good. Who knows? But we expect more supercontinents in the future as well. I like Amasia more as a name, but I think the concept of closing the Atlantic is more likely for a number of geotectonic reasons that we won't get into now. But we expect more of a Pangaea-like reconstruction. 250 million years from now, I will know for sure, and I know who was right. And so by that time, I'll let you know what the answer was. I think what happens is that I am still on the other screen. Sorry, let me get to my own screen. So one piece of evidence was we looked at mountain belts around the world, and people found out that there were the same age mountain belts over many, many, many continents around. They were just like the Cordillera, but not as these young surface deposits. They were a bit like the Appalachians, although the younger deposits were not there, but there was this narrow belt of an orogenic system. But in this case, these belts were made up of older rocks, obviously, because we're in the Precambrian, but particularly also higher metamorphic grades. We're looking at the deeper part of the lithosphere, that the stuff that got exhumed to the surface today, but all the cover sequence got eroded off. But if you start to do that, you could see belts of about the same age, about 1.1, 1.2 billion years, of all around many of these cratonic, many of these continental interiors. Today, it's not at the margin. I'll show you where it is today in North America in a second. Well, actually, I can show you that quite obviously on the map over here. We're looking at this connection right up here. This is where we are, North America. Now, what the blocks are? So here, North America is on its side. So turn your head over a little bit. You can see that Greenland is marked up there, and that's North America, Laurentia as we call that. And this thing called Amazonia, well, what that means, that is actually South American side to the east of the Andes Mountains, the Amazon system. The Amazon ecosystem is built on this block of Precambrian rocks. And so this is a part of South America that was in this configuration, has the same orogenic systems. We worked in these areas, we have got the same geology in Amazonia as we found up in Ontario. And we realized, of course, that these belts are very similar because they were, as we did in this diagram, they were connected in a supercontinent configuration when these origins were formed. Remember, the origin was formed when the two blocks were hitting, and so this is what this was. And so this Rodinia supercontinent, the mother of all continents, is based on the fact that we found these what we call Grenville orogeny type, and Grenville is not an H; it's a descriptor of an origin that we find in North America. We found all these belts in there. The diagram on the left is a little bit better. It just simply shows you in this lighter color right over here. This G on 10 to 11 means it's around 1.1 billion years old, and you can see that you can put these blocks and organize them, and so that they have, just like Pangaea does it in a younger history, had this configuration where these belts are connected to one another. And that sort of made us start to use the power of dating and the power of lithologic recognition. Of course, these are all metamorphic rocks now. You no longer see arcs and stuff like that. You see metamorphosed arc systems and the like. We can make this configuration. So this is the map of the supercontinent that is the best constrained as we go far back into the Precambrian, because as we get older we have fewer rocks, so it's harder to put it together. But this is the Rodinia supercontinent. And why this is fun for us to, why I picked this out to emphasize this in particular, not the Gondwana supercontinent, is that now we use the map of North America, and what we actually recognize is where this belt that we call this Grenville belt, and we're sitting, remember, we are, Michigan is right over here, there's an interesting place right over here, and this whole area right over here, this segment over here, and it goes into the direction, in that direction. That is actually the front of that old orogenic system, that Grenville orogenic system that was marking the collisional boundary between the Amazonian block on this side and the Laurentian block on that side, marking that collision of that, and made a mountain belt. And why is that amazing? Is, well, first of all, that's explained all the geology we have in Canada, but also we're sitting right up here, as you can see, and we were sitting 1.1 billion years ago, exactly where we have the front of the mountain range. What I always tell people, that if you would go back 1.1 billion years, and I have asked my physics friends to help me get this going, you would find Himalayan type mountain range sitting where Ann Arbor is today. And I look outside my window, little of that is preserved, but actually there were mountain ranges that were as big as the Himalayas. And we know that because the crust today is still 40 kilometers thick. It's orogenic crust. The metamorphism tells us we're about eroded down 40 kilometers. So we're missing 40 kilometers of top sequence. And so these were mountains as tall. The crust was 80 kilometers thick, which is what it is today on the Himalayas. And so a mountain belt that runs all the way through. So you can sort of continue this on into the southeast. It gets harder in the southeast because it's chopped up on much younger histories. It gets sliced up, and so, but it's really beautifully defined in the northeastern part of North America. We did a lot of work over the years in these orogenic systems, but change your mind. The Appalachians were not there. This white area that is on this map, this whitish area right over here where the Appalachians are today, that wasn't there. That's all much younger history. And the Cordillera, of course, right over here, wasn't there either. It's also much younger history. So you look at a very different shape of that continent. Some geology, because it's fun, it's nearby, it's worth a field trip if you ever get the time. You can just drive up. You go up to get into Canada, to go to the King's Highway. You start to go to Sudbury. Don't go to Toronto. Go to the Sudbury direction. You would find that most of the outcrops along your way are these brownish, grayish rocks that make up the Grenville gneisses, as we call them. It's a gneiss because there's not many schists. The metamorphic grade is amphibolite, or sometimes higher, so you don't have a lot of micaceous materials anymore. So the foliated rock, all deformation rocks, becomes a gneissic looking rock. But as you can see, there are lots of folds in there. There's a lot of deformation in there. This is the contact where we find the boundary between that Orogen called the Grenville Orogen. And as you go into Sudbury, and the road you see up here, if you keep going up in this road, you get to Sudbury. Actually, these high-grade rocks sitting right on top, if you go back a little bit along that road, right on top, these low-grade rocks that are older. They are Southern Province rocks, but they're unmetamorphosed, essentially, hardly metamorphosed sediments. And these very high-grade rocks sitting on top of that. That is a major detachment structure as well. So the Grenville is just like the Southern Appalachians. It's a major detachment structure that pushed these high-grade rocks on top of the margin of then North America, of then Laurentia. It gets a little complicated, we can build it up, but I want you to see those similarities. It's just an older orogenic system, just like the Appalachians, except we don't preserve the Appalachian type rocks anymore. It's all eroded off. We just see the deeper part of these rocks. So there's high-grade rocks, amphibolite rocks, sitting on top of low-grade rocks. That tells you it's the wrong configuration. That's what a thrust boundary is. It's called the Grenville front. It's the term there. Why I emphasize it here, that we are so close to the type locality of that. And I've showed you over the time, we talked about mylanites and stuff like that, these high-grade metamorphic rocks. Many of those samples came from the Grenville, because it's just a spectacularly exposed origin. But if you go there and you don't have the context, it looks like, well, it's just a bunch of gneisses, you know. Used to be called the Sea of Gneiss for that reason. So you go forward. And so the other feature that's very characteristic was this belt right up here. I'm going to go a little quicker because I see my time is running out. I have 5 more minutes technically, but please permit me to take a few more minutes. You can always stop this, and well, you can't stop it now, but I'll post the tape. But the mid-continent rift, which we talked about, is the attempt of the continent to try to break up. And that is a lot of basalt, but also, why is it fun for us? It is the source of Michigan's early wealth. The copper of Michigan, which made Michigan a very, very rich early state, was because of the copper that was found in these basalts, in these mid-continent rift basalts that were also collecting erosional material. So there are sandstones in there, and so hence these are conglomerates, and these are coarse sandstones, and they also concentrated the copper in there. This is where we got our wealth from. The failure of that mid-continent rift deposited first the basalt and the erosional products of that, and that's where we got much of our wealth from. The rift never made it, didn't succeed. 1 billion-year-old rift, it tried, but it didn't work out, but it left us with the wealth of the copper that is there. Copper Harbor is named after the copper conglomerate there that we find there. And if you go to Portage Lake, you find lavas, just like basaltic lavas. Those are these are the rocks that are the basalts that are associated with the rifting. We should go into the origin. Lastly, and I have 2 more slides left, just to get you, returning back to the flavor. Here's the map of Michigan, where we always make this commentary, well, there's not much to see in Michigan, a bunch of gravels. That's true. The surface is really not all that terribly well interesting for the structural geology. But if you would start to go a little deeper, or if you go to where everybody seems to want to have a cottage in Michigan, if you go to the northern part of the Lower Peninsula, you actually start to see some outcrops. At the bridge, we see the limestones are popping up. The lower Paleozoic limestones are popping up at the bridge. But it turns out that the entire substructure of the state of Michigan is this large, nearly perfectly spherical sequence of rocks, meaning they are a basin which is filled up, and another part of the basin filled up, another part of the basin filled up, another part of the basin filled up, with the deepest part of the basin nearly 5 kilometers, starting at the base of the Paleozoic. And the youngest rocks in that sequence are upper Paleozoic. So we have about from about 540 till about 300 or so million years, so 250 million years of deposition. The plate is not quietly sitting there. It only happens in this part. It's not all over the plate. It's not the rest as you wrote it off, only this Michigan part up there. And so we call these things intracratonic basins. Basins because they are depositional environments, restricted depositional environments. Intracratonic because the craton is that undeformable, is this strong part of the plate, not the plate boundary, but it's in the middle of the plate. So it's inside the plate, inside the craton, intracratonic. It's Paleozoic because of the age of that particular feature. There's also, it's not the only one, Illinois also has the basin in there. And in between are high areas, arches. So we have highs and lows and highs and lows. The plate seems to be pretty deformed actually. For a undeformable plate interior, there's a lot of geology, and that's the beauty of Eastern US geology. It's not boring at all. It actually tells us plate tectonics is not done when it comes to plate interiors, plate boundaries. There's also plate interior history. And the last map that I'll show you is this map that I showed in some incarnation, I think earlier on. I can't remember what detail it was, but it shows you this crazy on the right is the US, only the US side, and it shows all these features. And all these features are deformation features that are happening after this plate was formed in its current configuration. So after we generated the interior part of the plate, no plate boundaries there anymore, we still see a lot of deformation. I already mentioned the mid-continent rift. Well, that's a pretty big cut there. That's a big fault system. 20 kilometer of basalt was deposited there. So you mean you're cutting half the crust in there. We have these big basins sitting up there. The plate is generating basins. We find other basin sequences, Reelfoot Rift and places like that. We find later Precambrian basins in there. All through also we find fault systems, faults that are offsetting things. We find in some places significant fault displacements inside the plate. We even have, as you know, places where we find modern earthquakes. The New Madrid system in our interior in the plate. No plate boundary nearby. The only plate boundaries are old. There's nothing new in there, and yet the plate is deforming. So the deformable plate is actually a feature that doesn't get a lot of attention because most of the plate tectonic sees is action that today that takes place at plate boundaries. But every now and then, giant earthquake has happened also in the plate interiors. And this is what actually is a hazard argument we worry about, is that they may not be as common, but it's all the more risk when they do take place. But the whole history of the plate has been one that after it was formed as a consolidated, strong, rigid plate interior, deformation still continues on. And some of us have started to work on thinking about how is it possible to get all these features. Well, it turns out, this is why it's nice, you can actually link events that are happening on the Appalachian margin with features that are happening on the eastern side of North America. You can find features that happen on the Cordilleran margin, things that happen at the Cordilleran margin with features of deformation that happen on the western side of the plate interior. So what we're seeing, and we call that stress transmission, we're seeing that plate boundaries are obviously where the action is. But the stresses of these plate boundaries are able to go inside these cratonic blocks and still create all kinds of features, and sometimes dramatic features, that are still a reflection of plate tectonics. But whereas plate tectonics at the margins is horizontal, here much of the stuff is vertical. So if you want to simplify it, young interior tectonics is one more of vertical tectonics, but still it's linked with events that are with plate tectonics far away. So far field tectonics, as we like to call that. And so if you now wrap this up, it's 11:22, so I have a couple of minutes over, but go back to this map. Now when you look at that, I hope, I know there's a lot of information. You may have to replay some segments here, but I wanted you to look at this map and start to see, like, what do I tell people about this? Well, there's a lot of richness there. There are old origins, young origins, ancient origins. The Grenville that I didn't mark up would be right up here. That's the Grenville boundary right up there. I should put the G in there. It's an ancient origin. It no longer looks like an origin. That's why I don't mark it as an origin, but it's an ancient origin in there. And the origins also in the Southwest. But you start to see now how you make this continent. And North America is remarkably nice, obviously, because we live here. But also it has preserved much of that history. Other continents either don't show much in the younger history, like Africa. They have much of the old history. Only Australia is a bit like that, but Australia doesn't have the beauty what North America has as a Cordillera on one side and Appalachians on the other side. So the North American continent has been the deep playing ground to really understand tectonics. And it's not surprising, therefore, that plate tectonics today is understood everywhere, really found its roots and its acceptance in North America when things made sense to look forward to.